Okay, in this video, we're going to look at our new unit, which is about systems of equations and something called matrices. Matrices is actually the plural of the word matrix. So this whole unit, which is not terribly long, but it's about first reminding you about what systems of equations are. You did these in other courses. Basically, a system of equations is where you have multiple equations and they have multiple variables in them. So there'll be equations with more than one variable. You might have two variables, you might have 17 variables. Systems of equations of lower numbers of variables, 2 or 3, can be solved by hand, but doing ones that have a larger number of variables can be difficult. So that's why we're going to look at something called a matrix. Like I said, it's plural as matrices. A matrix is going to be a more efficient and more technology-friendly way of solving systems of equations, especially ones that are larger and more difficult. It's easier to actually let a computer do them through a matrix than it is to try to do them by hand. So this unit, half of it will be reminding you how to solve systems of equations like you did in other courses, and then the other half will be about what is a matrix, how does it represent these, and how does it help us solve these more efficiently with technology. So unit goal 1 is to remind you how to be able to solve a system of equations with 2 or more variables. This video actually won't get into the more variables. We'll just look at 2. And then in the next video, we'll look at 3. And then you'll see it starts to get really difficult to solve them. So that's why we move on to the matrix method, which allows us to solve it more efficiently using technology. All right, so when you solve systems of equations, there were 2 methods you were taught. One of them was called substitution, and the other was called elimination. We're only going to focus on elimination because it's the elimination method that gets generalized into what we call a matrix and then the matrix methods for solving it. Substitution can also be used to solve these, but especially as the number of variables go up, substitution becomes very difficult to do and harder to generalize. So we're going to just skip talking about substitution. If you remember that from algebra course is fine. But it's really elimination that gets the center stage and moves us into the matrix method. So we'll just look at elimination. So solutions by elimination involve doing this. Basically, you're going to have, for these simpler problems, there's going to be 2 equations with 2 variables, so like x and y. Now you could use this on something that has more variables, but we'll start simple. So the goal of elimination is to multiply the equations so a set of variables have coefficients that are the same except for their sign. So basically we want them to be the same numbers but opposite in sign. So we want like 5 and -5. That way they'll cancel out. The idea is once you get the variables to match except for their sign, you can add together the equations and it will eliminate one of the variables. So if you had 5x and -5x, those 2 things would cancel. And usually the goal of elimination is if you have x and y, you want to eliminate one of those variables, because once you have one variable, you can use regular algebra to solve the equation. The problem is when you have multiple variables, it becomes more difficult. All right, so I'm going to remind you of this solution by elimination. Let me show you a system of equations and then show you how it applies. So this is a system of equations. Basically, there are 2 variables. Our goal is to solve both of these equations at the same time. So we're looking for an x value and a y value that when we plug them into both, make them work. The problem with systems of equations is you have to have enough equations to solve it. So if I have 2 variables and only 1 equation, say they didn't give me the second equation, the top equation actually has lots of different x's and y's you could plug in to get -1. So one equation has lots and lots and lots of solutions. Once you put in a second equation, now not always, but most of the time, when there's a second equation, what it does is it knocks it down so there's only one set of solutions. In fact, if you have 2 variables, you have to have 2 equations in order to have any solutions. One equation's not enough to solve it. You need 2. If I had 3 different variables, I would actually need 3 separate equations in order to possibly have one unique set of solutions. And if I had 17 variables, I would need 17 equations. So solving 17 equations would be extremely difficult. This is why we want to learn about the matrix method and how technology can actually do this for us. All right, but before we talk about stuff that's super difficult, this is the easiest system of equations, because basically we have two variables and two equations. So we should be able to get a unique solution to these. The way I'm going to get the unique solution is to try to eliminate a variable. Now, it doesn't matter which variable you eliminate. I'm actually going to show you two different ways. The easier way is to get rid of the x's. So what I mean in the other slide is, how am I going to get rid of these x's? Well, what I'm allowed to do is, so if I can multiply the equation, I'm allowed to multiply it on both sides of the equation. If I do that in a smart way, I can make the coefficients match except for their sign, and then add them together and eliminate. So what I'm going to do is get rid of these x's. The way I'm going to do that is I'm going to make these two numbers match, except I'm going to make one of them negative. So 4 doesn't really need to be touched, but if I want this to cancel the 4, I could make this term here, where my finger is, into negative 4. How am I going to do that? Well, I'm not allowed to just change it, but I am allowed to multiply both sides of the equation. If I multiply both sides of the equation, it stays balanced, and it's equivalent to the old equation, and then I can work with it. So what I'm going to do is multiply both sides of this equation by negative 2. If I do that, it'll turn this into a negative 4, and then these will match, except they'll cancel due to their sign if I were to combine them. All right, so in elimination, that's what you do. You go, well, I want to make these things cancel each other. I'm going to give this negative 2. Now, I put the whole equation in parentheses. Basically, you're multiplying this side of the equation and this side of the equation all at the same time. So I'm going to multiply the bottom by negative 2. And what that's going to do is it's going to change this equation. Multiply everything by negative 2. You get negative 4x, negative 10y, or minus 10y, and then negative 6. So after doing that, this equation, after being multiplied, is the equivalent equation here. Now I'm able to eliminate, because notice that this is a 4x and this is a negative 4x. So I put this little plus sign here because once you have them opposite, you can eliminate the variable by adding the equations together. So I'm going to take this equation, add this equation to it, and these x's will go away. So what happens is, when I add 4x to negative 4x, comes out as 0x, so it's gone. 3 plus negative 10, because I still have to do the rest of them. So when I add the 3y to the negative 10y, remember when you add a negative, you subtract. 3 minus 10 gives me negative 7. So I have a total of negative 7y. And negative 1 plus negative 6 makes negative 7. So this is the part where I eliminated the variable. The x is now out of there, and once you have one variable, you can solve the equation using algebra. So what's left is this equivalent equation, negative 7y equals negative 7. So I'll divide both sides by negative 7 to get rid of that negative 7, and I get that y is 1. Now, I got one of the answers. The problem is I need both variables. So once you get one of the variables, that y is 1, you can do what's called back substitution and basically use this in one of the original equations. You can actually use it in any equation, but it helps to use in the originals because if you make a mistake somewhere, you don't want to use one of the equations you might have made an error on. So I'm going to go back to one of the original equations and use that y is 1. Now, it doesn't matter which, well, there's your answers. It doesn't matter which one you use. I'm going to, I think I'm using this one. But you can plug the y into either equation, then solve for x. So kind of flash the answer. Let's see it for real now. So basically, I chose the 2x plus 5y equals 3 equation, which was that one. And I'm going to plug in what I know about the y. Nice if this thing worked, right? So what do I know about the y? Remember, the y is 1. So once you plug that in, you're able to solve for x. So this is called back substituting. I'm taking what I already know and putting it back into one of the old equations. So once I put this in, this is 5. 5 times 1 is 5. Subtract the 5 over, because now I want to solve for the x. Subtract the 5. 3 minus 5 is negative 2. I'm left with 2x equals -2, so then divide 2 on both sides and you get -1. So I get y is 1 and x is -1. You want to report that as your solution set. So those are the two answers I was looking for. And if you want to check them, you can. You don't have to, but if you want to make sure you're correct, you can see if these actually work. So x is -1 and y is 1. If you try them back in the original equation, you'll see that they work. So if you make this -1 and this 1, you'll get -4 plus 3, which is -1. And if you make this -1 and make this +1, you get -2 plus 5, which is 3. So that set of x and y work. No other pair of x and y would work. So those are the answers to the equation. Now, for more difficult ones, I only had to change the one equation. I'm going to do this problem again, but instead of the x's, I'm going to do it with the y's. So let's pretend we didn't solve it already. And not all the time can you just get away with changing one variable. Sometimes you have to change both. So what I'm going to do is redo the same problem, so I should get the same answers, but I'm going to do it by getting rid of the y values. If I wanted to get rid of the y values, I have to multiply both equations, because I can't just turn 5 into 3 or 3 into 5 very easily. I'd have to multiply by a fraction. So it's easier to multiply so they both turn into the same number. Well, if I give this 5, it'll turn to 15. If I give this -3, it'll turn to -15, and they'll match except for sign, and then they'll cancel. So if you don't want to get rid of the x's, you could also eliminate the y's. It's a little more work in this particular problem, but it doesn't really matter how you do it as long as you do it correctly. So I'm going to show it again. Let's cover up some of the work so I'm not overloading you. So what I'm going to do is try to eliminate the y's. Once again, I already solved it. I'm just solving it again to show this method. If I multiply everything by 5, it'll turn this into a 15. Multiply everything by -3, it'll turn this to -15, and then the y's would cancel instead. So if I do that, here are my results. This turns out as 20, 15, and -5. And then this comes out as -6, -15, -9. So once I have the new equations, notice these will cancel each other. I'll just add them together. So I have this plus sign here showing I'm going to add the two equations. The result I get when I add the two equations is, well, the 20 plus the -6, 20 minus 6 is 14. 15 minus 15 gives me 0. So I have 14 x's, 0 y's. And when I add -5 to -9, I get -14. So I should get the same answer I did last time. Last time we got x was -1. Well, if I divide the 14 on both sides, I get that x is -1, just like it was last time. And just like last time, I keep flashing the future answer. So once I know x is -1, once again, I can back substitute into either equation. I decided on this one to go back to this original equation because I used this one last time, so I'll use this one. Basically, take the value you found, choose an original equation to put it back into. So this time I chose the 4x plus 3y equal -1. Plug the x in, and now you can solve for what y is. Well, this comes out as -4, so I'll have to add it over here. If I add 4 to the other side, I'll get 3, and then divide the 3's, and I get y as 1. So notice I get the same solution set. I would choose the easier way if possible. So the first one I showed was easier to do than this because I didn't have to do as much work. However, it doesn't matter which way you do it. And just to beware, the reason I showed this is because here I kind of got lucky that I could change the x just one time. A lot of times you have to change both equations to make them work. So if the two numbers don't work well together, 3 and 5 are both prime. So if they don't work well together, you may have to multiply both equations at the same time. All right. So this is basically a reminder of how to solve two variable equations. The last thing I'll do is show a word problem, because basically in math, why do we care about any of this? Well, in real life, there can be many variables under many conditions, right? You can imagine if you were studying maybe people, you could have all kinds of things about them: their weight, their height, their level of education, how much money they make, how old they are. I mean, you could have lots and lots of variables. If you want to study how those variables might affect things, you need to be able to use systems of equations. So studying 30 variables at the same time can be very complicated. So we'll look at simple examples of, once again, 2 variables. So here's a simple example and how to set up a system of equations and use it to answer this question. Now, if you're good at math, you might be able to solve this without it. My point is to show how it can model it, and then when you get more complicated questions, to see how these things model them, and then later how a matrix and technology can do what normally a human would be able to solve very easily. So once again, you might solve this without it. This is just a simple example to illustrate. So if we read it, it says, last year the number of juniors in Math 12 was 30 more than the number of seniors. Total enrollment for both grades was 78. So they want to know how many in each grade it took Math 12. So how many juniors were there in Math 12 and how many seniors? They've given us some information, basically that there were 30 more, the juniors were more numerous, there was 30 more of them than the seniors, and then when you put them together, you get the number 78. So there's a total 78 enrolled altogether. So the first thing, if you want to solve this using algebra, is to basically define your terms. So I'm going to let x equal the number of juniors and y equal the number of seniors. Now I want to make my equations. Well, I need 2 equations since I have 2 variables. So I'm going to start by trying to make the 2 equations that I need. So the first equation will come from the first piece of information. That basically, in order to make the juniors and seniors equal, I would actually need 30 more juniors, right? Juniors and seniors are not equal to each other. There are more juniors and seniors. There's also the fact that if I put the juniors and seniors together, I get 78. So to make the equations that I need, I'm going to use both of those pieces of information. Now remember, the juniors outnumber the seniors. So if I want to make them equal, I would have to add to the number of juniors. So the way I'm making this equation, I'm saying, well, basically, if I take the number of seniors and increase the number of seniors by 30, that matches the number of juniors, and that's what they said in the problem. So be careful that you don't add the 30 to the x, because it's the juniors that are more numerous. So I'm going to take the seniors, add 30, and if I were to do that, that would match the number of juniors. So there's an equation. The second equation says if I added the juniors and seniors together, I should get 78. So the goal here then, if the equations aren't lined up, like I want x, y, and equals. Notice that the equal sign's here, x is by itself, and then over here the 78's by itself. Basically, I'm going to move that y value over, so I have the x's, the y's, and the numbers lined up. So if the equations aren't set to go, you kind of need to rearrange them. So I did that in the next step. Basically, yep, there's the answer again. Basically, what I did here was move the y over, so I got x minus y equals 30, and x plus y equals 78. Now, normally then you'd have to multiply for the elimination, but notice that these both are ready to cancel. This is negative 1y and positive 1y. So be on the lookout. If it's already set to go, there's no reason to multiply anything. So these are ready to cancel, so I can eliminate them. So that's why I put my plus sign here. I'm going to combine them. X plus x will give me 2x. Realize these don't cancel, they're being added. But negative 1y plus 1y will give me 0y. They will cancel. Then adding these together, I'll get 108. So that's my next equation. I get 2x plus 0y equals 108. Divide the 2 on both sides. I get x is 54. Now remember, x represented the number of juniors, so now I know there are 54 juniors. Now I can back substitute into either equation. I'll use this one. So 54 plus y gives me 78. If I use that, 54 plus y gives me 78. I can solve that by moving the 54 over. If I do that, subtract 54 from 78. It'd be nice if this thing worked right. Gives you 24. So that's the solution to my system of equations. And notice it also solves my problem. So how many juniors and seniors were there? There were 54 juniors and 24 seniors in the class that year. Basically, if you add these together, you get the total number 78. And notice that the juniors are 30 more than the number of seniors, just like they wanted. So this is a way that a system of equations can solve this kind of problem for you. Basically, it requires you to be able to organize it, though, into equations, and then to set those equations up as a system and then solve them. Now, in real life, because I said you may have been able to solve this without the system, usually what happens in real life is there are a lot more variables and a lot more information, And usually people don't solve them by hand. We'll see later when we get more complicated how a matrix can also solve this. And if you know how to use technology, you don't actually have to do anything but enter enter the numbers, and it'll actually do everything for you. All right. But for now, that's enough. So look to the assignment. It will have basically two of these, solve it with no context, and then there'll be one problem that is in context, so you can see if you could set up the system and solve the problem. All right. Well, that ends this video. Next time we'll look at what happens if there are three variables, which is more complicated. Until next time, see ya.